No, it's not.
All right, can we not?
No, it'll take like just a minute.
All right. So we're going to learn about perpendicular bisector theorem and then prove that perpendicular bisectors of a triangle are always concurrent, okay? So perpendicular bisector theorem says if you have a perpendicular bisector, which we do, right? This line right here does perpendicularly bisect this line right here because it bisects it and leaves it at 90 degrees, right? Cool with that? Then we know that any point on this line will be the same distance to the endpoints of this segment, okay? So the distance from here to here and here to here will be the same. Any point I draw on here will be the same distance. If I put a point like this on here, then the distance from the endpoints to that point will be the same. Always. At any point on there. And as I go down this flagpole, right? I keep going down and down and down. This point would also even be equidistant to the endpoints. And look, it is, isn't it? Right? Right? So the idea is that the midpoint, right, equidistant from both endpoints. As you go up the perpendicular bisector, it's still going to be equidistant. Okay? So we're going to prove that. So we're given that D is on the perpendicular bisector of ABC. And it is, right? That's a perpendicular bisector because it's perpendicular. And it bisects the side. If you can't see these because they're kind of light, that's what's given to us, right? And that makes sense. Perpendicular bisector, ABC. Cool? All right. We're going to prove that D is the same distance from A and C, the endpoints. So first off, let's talk about this distance from A to D and D to C. So let's say let there be, let AD and let CD. Cool? Right. So I'm just creating those. We go with that? Awesome. So I'm going to prove that these two are the same distance, otherwise known as they're congruent, right? Does that make sense? Well, we have two triangles here. How are we going to prove that these two blue lines are congruent? What do you see? Spoilers, we get this for free, right?
Side, angle, side.
It will be side, angle, side, right? Where's that last side? I got side, angle. Where's the last side?
The shared
side.
The shared side. So by shared side, BD is congruent to BD. We cool? Are we all back? Or are we still missing one? Okay. So shared side. And then by side, angle, side, these two triangles are congruent, right? You can draw the congruency symbols there or not. I don't care, right? Triangle ABD must be congruent to triangle. Can you close the door behind you? CBD. Nice. Nice, nice, nice.
Elaborate. I don't get it.
Well, so these two triangles are congruent by SAS. And if the triangles are congruent, then shouldn't their parts be congruent? What do we do to say their parts are congruent? CCP, right? Corresponding congruent parts, right? Because we're talking about congruent triangles. So by CCP, we know that these two sides are congruent, AD and CD. Why? Because they're corresponding, first and third, right? Corresponding parts will be congruent. That's what this means. So AD congruent to CD. Now, if AD and CD are the same length, doesn't that mean that D is equidistant from AC, A and C? Right? So by definition of equidistant, right? D is equidistant from A and C. How do you feel?
Seems fine.
Basically, this is a proof that we did for like quiz 2, right? Prove triangles congruent and then get their parts, right? Now, the beauty here is that all this work is now in a theorem, right?
So you're just saying
The theorem is perpendicular bisector theorem. So instead of doing all that work to prove these two sides the same, whenever you have something like this, by perpendicular bisector theorem, those sides are the same. Done.
question.
Okay? That's powerful, right? Yeah.
Could you also say angle side if you said that angle A and angle C are congruent?
You don't know they're congruent because we didn't have that yet. We don't know they're congruent. They will end up being congruent. but we didn't know that. There's no way to prove that just given this. Okay. After you get the triangles congruent, yep, they will be the same, right? A and C,
Did all the work.
right? But it's all in the order, which is why it's really important, especially in geometry, for you to watch what's going on and not just look at the end result, right?
Wait a minute.
Because it looks like, sure, we could say A and C are congruent, right? Isosceles triangle theorem. Converse. No. Theorem, right? But again, it's the order that matters, right?
So this is just what we did before, then restating the question at the end of it, right?
Well, we always say what they want at the end, otherwise we're not done. That's how we know we're done. Yeah, like 3 or 4 weeks ago. And it feels really easy now, doesn't it? Now, we had to draw in our own lines, but like, yeah. Like I said, if you understand something, the more time goes on, you'll get better at it. If you memorize something, you'll forget, which is why those of you that actually know your crap will be better on the final than you are right now. You really will. Yeah.
How come this might be kind of stupid?
No, it's okay, please.
How come
Please.
you have to draw in your own line?
Well, we want to prove that D is the same distance from A and C.
Yeah.
So I wanted to draw lines that represented that distance. Right? That's all. And if those lines are the same, then the distance is the same, right? What's the shortest distance between two things? A straight line, right?
Okay.
Cool. Great question.
Wait a minute. Never mind.
Okay.
Well, no.
So that's the deal. That's why this is true. Whenever you have this, any dot on that will get the same result, right? It'll be the same distance from the endpoints. Are you sure? Because it's important.
Why can't you just make a square, but then you need another 2 points to do that, and that's like.
Because making a square is an extra step.
Yeah, so instead of.
You could do a square, but how would you know these sides would be the same as this side? Right? Yeah, it's not stupid, but it's good to realize that that doesn't work. Like, I know it's silly, and Einstein's a total, or not Einstein, Edison's a total douchebag. But his thing about like, I found 999 ways to not make a light bulb, right? Before I made one, right? So even in your failures, like the mistakes, right? That's good because it expands your brain. You know why that doesn't work.
He had 9.
Yeah, he was a douche. All right, so anyway, moving on. Nikolai Tesla. Yeah. Serbia. All right. What?
Are we going over an order like that?
Yeah, it's just the converse. So the theorem says if you have this, right, if you have a perpendicular bisector, then you know any point on here will be equidistant to the endpoints, right? The converse says if you've got this, then this point must be on the perpendicular bisector.
Dude, I am not looking forward to this.
This is easy. No?
You should probably put your phone away then.
Isn't this easy now?
I'm learning about it.
Multitask. In my class. Okay, well, I mean, if you're not worried about the review, then I guess it would make sense to multitask because you're good to go. Wait a minute.
You are.
Contradiction.
I'm doing the
Just what
Contradiction.
I am the teacher.
See, I'm learning.
Lightning bolt, dot. All right, so here we go. Perpendicular bisector theorem, converse. All right, so it says if we have a point that's equidistant to the sides of another segment, then that means this. That point must be on the perpendicular bisector. So if I draw the perpendicular bisector, it'll go through that point.
Ruler.
Nope, I'm not going to do it for real, but we just know that it should be, right? Based on this theorem. Right? And again, if you just looked at this now instead of watching me draw it and why, it's going to be really confusing to you. If you watched while I did it, then it makes sense why this is true, right? If you have that, then you get this. Okay? Yeah.
So equidistant, does that mean it's equal from the sides to?
Yeah, equal distant, right? It's the same distance from this point and the same distance from this point.
All right.
Right? Does that make sense? So if you have it equidistant, then it should be on the perpendicular bisector. Cool. All right. So we're going to prove that D is on the perpendicular bisector of this triangle, right, of AC. We're given that D is the same distance from A and C, right? See how that's drawn in for us? We cool with that? So, now, before we get going, okay, you are allowed to assume two of these three things whenever you want. Watch this, okay? Here's a triangle. Do all sides have a midpoint?
No. Yes.
Yeah, there's always a halfway point, right? If you look at the small, just halfway, right? So, let's say this is the midpoint. That's totally valid. You can say, look, let D be the midpoint. I know it exists somewhere. Let's just say D is it, okay? Like, I don't want to get my ruler. I know it's somewhere. Let's just say it is, right? And then you can connect dots, right? That's totally valid. You can assume this. That's fine. Okay? You can assume this, right? If I give you a line, can you draw a line that's 90 to that?
Yeah.
Yes, always, right? So I did this, and somewhere it's gonna hit it at 90, right? Over here it's not, over here it's not, over here it is, boom. Let's just say it is, right? That's totally valid. Saying that vertex to 90 degrees. Totally valid to assume that, okay? To say let there be, okay? You're also allowed to say, look, this is the midpoint, I'm gonna go straight up from 90 from there.
That's
Totally valid. So you can say, look, let this be the perpendicular bisector. You can say, let this be the orthogonal. Let this be the median. Totally fine. What you cannot do is this. You cannot say that this is the midpoint, this is 90 degrees straight up, and that's 90. You can't say that it's connected to the vertex, 90 degrees at the bottom, and the midpoint. You can't do all three at once. Because there's a triangle, right? Plenty of triangles that don't do that, right? Does that go through here? No. If you tried to say it did, that's fine, right? That's totally fine. So that's fine. But you can't also say that's 90, right? It's not true in all cases. You can't assume that. So you can assume that it goes from vertex to midpoint. You can assume it goes from vertex to 90. You can say it goes from midpoint up to 90. But you can't do all three at once.
Wait a minute.
So this is vertex to midpoint, right?
That's not right. That's not 90, though, is it?
I know it's not. That's my point.
Okay.
So assuming vertex to midpoint, totally cool. Assuming vertex to 90, totally cool. Assuming midpoint going up at 90, totally cool. But assuming on a triangle, vertex to midpoint also at 90, can't assume that, right? Here's a triangle where that's definitely not true, right? One of these at a time, totally fine, right? Two of the things, right? These two, these three, these two, but it's not all three at once. Do you see that? You can't assume that, because here's a triangle where that's not the midpoint, right? Definitely not.
What if it is a triangle where that's the midpoint?
Well, if it was the midpoint, it'd look like this. And would that be 90?
It's a different type of triangle.
Now, there is a certain triangle where it's all the same, right?
Did you just make that?
Okay? But does it work for all triangles? Those with me, those with me. Some triangles have vertex midpoint at 90. That's fine, right? Where it all plays into itself. It's called an isosceles triangle or equilateral. But aren't there other triangles where it's not going to be vertex midpoint at 90? Right? See what I'm saying? We cannot assume that. We can assume these, right? That's true for any triangle. But all at once is not true for all triangles. It's true for some, but not all. Okay? So what I'm going to do for this one is I'm going to drop a perpendicular. That's totally valid, right? We can say, look, vertex to 90. That's totally valid. I'm going to assume that's fine. You could also say, let this be the midpoint and connect the dots. Totally valid, right? What we're going to do is do this first one. So I'm going to drop from here to here
Question.
at 90. Yep.
So you're dropping it because we're trying to prove that it's perpendicular?
So I'm trying to prove that if I draw a line from this dot down, that it'll be 90 and the midpoint. All three at once, right? I assumed the first two, going from here to 90. That's totally valid. Every triangle has something like that. What I'm going to prove is that last little bit, that these are equal. Okay? Well, I mean, you can ask it again. I'm sorry I misunderstood. That wasn't on purpose.
Why did you draw the 90 because it's asking for you like to prove that it's
So I want to prove that if I draw a line from this point, that line will be 90 and cutting the other line in half, a perpendicular bisector, right?
okay.
So I assumed the perpendicular part, and I'm going to prove that it bisects. Now, you could also assume it bisects and then prove the perpendicular. That's fine, right? Okay, it's kind of weird, but you'll be okay, yes. Okay. So I need to prove that the line that goes from here to the opposite side is 90 and cuts it in half. So I assume the 90 part, right? That's totally valid. I can assume a 90, right? So what I need to prove is that this is true, that these two are congruent, okay? It can happen, but only in special cases. So you can't assume it, because it's not true in all cases, right? But I can prove it for this case.
It's like HL.
Sloffer?
I was going to ask, since, can you do this from any
vertice or vertex on the triangle? I mean,
Only when the sides are congruent.
so could you do it on C right now if you want?
No, because we don't know these two sides are congruent.
Oh, okay.
Yeah.
So you can only, that only occurs occasionally?
This only occurs occasionally. It's when these two sides are the same. It'll always happen. That's what we said, right? Okay? All I'm assuming is, look, I'm just drawing a perpendicular. That's totally fine. We do that all the time, right? Here's a line, draw a perpendicular to it. Done, right? So it's okay that I'm assuming that. That's not the point of this. I just want you to know it's okay. Okay? So I'm going to say let BD exist and have it be perpendicular to ABC. I included the B in there so you know where it intersects, right? That's important because there's lots of ways to draw perpendiculars. Okay? So I said let there be this. Now I have two triangles, right? And I can compare them and do some work with it. Before I only had one triangle. Is that cool? So I get this for free, right? I want to prove that these two segments are the same. Because if I do, then that's a perpendicular bisector, right? It's not just a perpendicular. So what do I have to do, Rosie?
The isosceles.
Yeah, by isosceles triangle theorem. Do you see how it's isosceles? So I get this angle and this angle by isosceles triangle theorem.
Segmentation. So like use
No, stop.
No.
That's cool. Just not in here. Are we good? Right? Now I'm going to prove both those triangles congruent, and then therefore their parts must be, right? And then I win. So how do I know those triangles are congruent? Angle, side, or side, angle. I don't care, right? Laney?
Wait, never mind.
Okay. By angle, side, right? These two triangles are congruent. I'm going to go ABD, congruent to CBD. Nice.
So we don't know that B is the midpoint.
We don't know B is the midpoint. We're going to prove that it is, right?
Is that the fun? This is gonna help with my other test, I think.
A little. So, angle, side, these triangles are congruent. And if they're congruent, shouldn't their parts be congruent?
Yes.
So what do I do? By CCP, corresponding congruent parts, AB and BC. Are they corresponding? Yep. So AB is congruent to BC. So, was DB a perpendicular bisector?
Yes.
It was. It wasn't just a perpendicular. It ended up being a perpendicular bisector, right? Because it bisects and it's perpendicular. So by definition, BD is the perpendicular bisector. Here's my symbol for perpendicular bisector. Are we cool with that?
We just like the word.
It's a big word. Words are hard, right? Perpendicular bisector. Of AC. Right? That fits the definition of perpendicular bisector. It bisects and it's perpendicular to AC, right? Now, we need to prove that D is on that. Well, is B on this segment? How do you know that B is on that segment? Because it's in the name. How do you know that D is on this segment? Because it's in the name. So how do we know D is on this? Well, it's in the name. So we just write, therefore, D is on the perpendicular bisector of AC. That's it. No reason given. It's just because it's in the name, right? We know a point's on a line if it's in the name of the line. Okay? And that's it.
D is on the perpendicular.
Now, again, why am I allowed to assume that that's perpendicular? All lines, or all triangles are going to have a perpendicular somewhere. I just said let that be it, okay? You could have also, before we go on, you could have also done it this way. It's up to you. If you're given this, you can say, let this be the midpoint, right? Don't all lines have midpoints?
Yes.
So let that be the midpoint. Am I allowed to connect dots?
How can you say that's a midpoint though?
Well, the midpoint's somewhere.
So
he just says-
So I said just let D be it, right? Wherever the midpoint is, let's call it D. That's all I'm saying.
Yep.
All right? And then I connect my dots. And then you can prove these are both 90, and that's a perpendicular bisector, right? How would I prove those are both 90? Well, isosceles triangle theorem, right? Side angle side means the triangles are congruent. Their parts should match up. Turns out these angles will match up. If both of those angles are congruent and they're a linear pair, let's call them angle X and angle X, right? They're congruent.
You made a face.
And they have to add up to what? They're a linear pair, they have to add up to what? If they're a linear pair, what do they have to add up to? 180. Well, if they're congruent and they add up to 180, what does X have to be? 90, right? So those are 90, and they bisect. So this is a perpendicular bisector, right? So whatever way you want to do it, if you like to draw the midpoint first and prove those are 90, great. right? If you'd rather assume it's 90 and then say those are congruent, go for that too. It's up to you. You guys see why that's true? Again, we can't assume all three to be true, right? Because that's not always true. Here's a triangle where it's not 90, right? Something's got to give. But one of these is fine.
So you don't have to prove that D is the midpoint, you can just pretend it is?
Yeah, you can say let D be the midpoint, right? Every line segment has a midpoint.
Yeah,
Instead of measuring it, just say, look, pretend D is, right?
alright.
That's fine.
Technically, you're just.
Every triangle, every line has a midpoint, right? And we can connect dots. Every triangle has an orthogonal, right? No big deal. Every triangle has a perpendicular bisector, right? It's when the perpendicular bisector goes through the vertex that you have the issue, right? You can't assume that. All right, I want you to focus on this. We can assume this. Are we good? We can. We can't assume it also goes to the vertex, right? We can't do all three. But these two are fine. Are we cool with that? We're going to use that. All right. Page 12. We're going to use the perpendicular bisector theorem to prove that all of the perpendicular bisectors of a triangle are concurrent, all intersect at one point, right? So here we go. First, we got to create some perpendicular bisectors here, right? There aren't any. So I'm going to create some. So we're going to say let there be. I'm going to go from here. Well, let's actually do here. Let's do here. I think it'll be easier for you to see. I'm going to say let that be the midpoint, essentially, right? And I'm going to draw straight off at 90. So, I don't know. This looks like 90 to me. Notice I'm not assuming it goes through A, right? I'm not assuming that, because we can't. That's totally valid, right? That's totally valid, right? All lines have a midpoint, and you can always draw a 90 from another line, right? That's cool. Some, what? What's, why did I what?
Why is it not even with A? Why is it not meeting with the A?
We can't assume all three, right? If you're going to draw a 90, you can't assume it goes to there, right? And it turns out if you look at my drawing, it actually doesn't, right? But we can't assume all three, right? Good question. Now, I'm going to draw another one in on this side. So let's assume this is the midpoint. We'll call it, actually, let's make this E, right? It's got to go somewhere. Let's make this F. And I'm going to draw from 90 like this. Cool. Totally valid, right? Now, these intersect at some point. That's true, right? I'm going to call this G. And I'm going to say they intersect at point K. I'm just picking letters, okay? They do intersect at some point. That's a fact. If I draw this last one in, this last perpendicular bisector, I can't assume it goes through K. I could say it does intersect this guy at some point. It would intersect this guy at some point. I'm going to prove that it has to be K when I draw that last one in, okay? But for now, we're just creating these guys. So I'm going to say let DKE exist and have it be a perpendicular bisector of BC. So I'm going to do this, perpendicular bisector of BDC. We cool with that? So I drew this guy in and I wrote it. We cool? And I'm going to draw this guy in. So I'm going to say let FKG be the perpendicular bisector of AFC. So all that means is what I drew, right? And see how they share K? It's because they intersect there. Yeah.
Would it mean anything if you drew a line from C through K and hit the other side? You know what I mean?
Not necessarily. No.
Or not from C. There's from F to D. Would that mean anything?
Yeah, because this right here and this here are congruent. That'd be called a mid-segment, but we're not going to worry about that. Okay. All right. So is everybody cool with what I wrote? Right. Draw a line that's perpendicular to this. Draw a line that's perpendicular to this. I made sure to include K in there so you know that that's where they intersect, okay? Now, the last one I can't draw it through K and just assume that, right? That's not cool. I need to prove that it would have to go through K if I did the perpendicular bisector here, okay? So what I'm going to do is this. Isn't K, let me turn the diagram. We'll try it this way.
Can I go to the bathroom?
Yes. It's not in here. Isn't K on this guy's perpendicular bisector? So we know by perpendicular bisector theorem that this distance and this distance should be the same, right? So this and this is the same, right? So by perpendicular bisector theorem, by perpendicular bisector theorem, CK congruent to BK. We cool with that? By the same theorem, isn't K on this guy's perpendicular bisector? Right? Isn't K, this is point K, it's just upside down.
Yeah.
Isn't K also on this perpendicular bisector?
Yeah.
So any point on this perpendicular bisector should be perpendicular to its endpoints. I'm sorry, equidistant to this endpoint. So we already got this one, right? So I get this one as well. They're the same length. Are you with me on that? The same logic. The diagram's getting crazy, but if you're watching, it shouldn't be too bad. So that means those are all congruent to AK as well.
40. Yeah.
All right. We cool? Sorry, it's gross. Now, here's the thing. If K is equidistant from A to B, and didn't I just prove that? Right? Right? Then K should be on the perpendicular bisector of this side. I'll go back. If we have this, then that dot must be on the perpendicular bisector, right? Seeing it? Well, I just proved using the other ones that we do have that, right? So K is going to be on the perpendicular bisector of this side. So if I were to draw it in, it would be on it. That would be the perpendicular bisector. Because it's equidistant, right? Now that's the converse, right? So by perpendicular bisector theorem converse, since K is equidistant from A and B, then it's on the perpendicular bisector of AB. So K is on the perpendicular bisector of AB. Well, hold on. If K is on AB's perpendicular bisector, and it's on BC's perpendicular bisector, and it's on AC's perpendicular bisector, all our perpendicular bisectors intersect at K, don't they?
That means it's concurrent.
They're concurrent. Therefore, by definition, the perpendicular bisectors of triangle ABC are concurrent at K, but I'm just going to write concurrent because that's all I wanted. All right? I'm going to go over it again. If you want to copy stuff down, now's the time to do it if you're getting it. If you're not getting it, now's the time to watch up here. Okay? I can't wait till I have that.
Wait,
camera.
time out, Mr. Mack.
What key?
Are the blue lines up there, are those angle bisectors?
No.
They're not?
They're not.
All right.
They're not. All right, so here's my triangle.
I'm gonna go whiz.
I'm going to assume that this is the midpoint, and that's perpendicular. I'm going to assume this is the midpoint, and that's perpendicular. They intersect at some point, we'll call it K. Okay. Well, because this guy's on this perpendicular bisector, it should be equidistant. I know this is the bad drawing. From those two sides, right? And if I know this is on this perpendicular bisector, it's equidistant from these 2 points. So those are all the same.
And then you got
And then if it's equidistant from these two sides, it must be on this guy's perpendicular bisector, right? So they're concurrent K. I'm gonna do it one more time. Here's a triangle. The closer I make it to a right triangle, the more likely it's gonna end up on here, but that's okay. I'm gonna assume midpoint here, perpendicular. I'm gonna assume midpoint there, and a perpendicular. They intersect here at K. Because K is on this guy's perpendicular bisector, right? Here's the perpendicular bisector. Here's this guy, right? He's going to be the same distance from here to here. Is everybody seeing that? By perpendicular bisector theorem, yes? Okay. He's also on this perpendicular bisector. So he's the same distance from this point and this point. Which then gets us our bottom guy, right? Same distance here and here. By the converse, our perpendicular bisector must go through K. So they're all concurrent at K. No? Or yes? Goes like yes. Okay. Are we feeling decent about this, Katie? Yeah? Okay. Sixth hour always gets the best show. If you're watching and you're not in sixth hour, this was the best show. Watch this one if you were confused earlier.
Great.
I always have to adapt to however your minds are. And today your minds are more like this than what I showed first hour. God rest their souls.
Why?
First hour. They're my guinea pigs every day, right? I have planned second hour, and so I get to see what happened to them, and I go, oh God, never again. I've committed war crimes, right? And then I decide how to not do that, and then by the time I get to sixth hour, I have the perfect lesson, right? And my rowdiest class, so it kind of evens out. All right, so, yeah. All right. How you feel about that?
It's because
It's 1:30. All right.
Eastern time?
We've got 12 minutes left. I'm going to give you 2 minutes break, and then I'm going to hit the next one, okay?
Great, I can get a can.
I have been dreading having to teach you this for a while.
Does this break include writing?
Orthogonal's concurrent.
Can we not?
No.
Bro, I can't do it.
I'm not going to teach you it today. I'm going to show you it. That way when you get it tomorrow, it'll be the second time, okay?
What's the answer to that one? The writing question.
If you want to copy down what I had, now's the time to do it, okay?
I'm good. I'll write it down when
I think we can get a game of chess in.
No.
He is not playing.
And the reason you need it written down is I want to give you 3 points, right? I know that kind of sucks because like it's hard to write during my class, but I also want to give you 3 points. I'm very lenient grader. Okay. Yes. For this guy?
I can't ask you for help.
No.
Oh my god, see? Mad at him?
No, I can't ask him for help. He told me
But I don't need
taking
math.
the quiz. Review packet.
Care about
His help.
Yeah. You know who's running? If you can't do it, then we'll go on the review packet and just come in and ask him. I think that's smarter than just taking the quiz. That's what I do.
No, he told me that if I don't want to take the quiz, I'm do the review packet.
Yeah.
But I can't ask him any questions.
I don't know. You ready?
Yes.
For sure. Time. I had all these kids complaining about why did you get my grades and why did you get it? And it's because I'm too busy grading all these retakes, which some of you end up bombing. Just like, oh, I'm fine. And then you're not. But you're okay?
That's what I said.
What quiz number was it?
3.
Was it the one with triangle congruency, triangle similarity,
How's your
the
birthday?
definitions we just did?
Yeah.
The definitions, so quiz 4. Okay, yeah, you'll be all right. Quiz 4 is the easiest retake. It's the hardest to take the first time, but it's the easiest to retake.
Wait, did you grade it?
Quiz 4? Yeah. The one we graded last Friday in class. All right, guys, I'm going to pull you back in now. I'm going to show you. Wait, do you need to copy more down?
Hey, when did you go back?
I gave you 2 minutes.
I know.
You good? You good? All right.
Wait a minute.
So,
Hey, language.
I don't know what you're talking about.
We'll put you in the hot box. Not hot box, though. What's it called in prison? You get sent to the thing in
The X house?
really weird.
All right, sit down. All right. I'm going to save this one for when we do it officially tomorrow. Tomorrow we'll wrap up with this, and then we'll do some application of some of the theorems we learned, okay?
Application to Applebee's.
We take a trip to
Do you have open bowling?
Let's see. I need to get a small triangle. All these others are interchangeable. I just need the small triangle. There
I
we
didn't
go.
even see that triangle.
Okay.
Do you have open
All right.
bowling?
So I'll save that for when we do it for real tomorrow. I just want to show you the logic, okay?
Yes.
Before we get to this, do you guys remember a while ago
Maybe.
we said that if we have a triangle, this is kind of what Schlaffer was talking about,
Yeah, you know stuff.
and we find all the midpoints, right? Let's let these be the midpoints. And we connect them all, right?
Oh,
We get the triforce, yes. So remember, we proved that this triangle on the top is similar to the big triangle, right? In a relationship of 2 to 1. And we proved that these guys are parallel, right? And that this is double and this is half. Do you guys remember that, right? This is twice as big. That's half of it. That's twice as big. This is half of it, right?
That was not too long ago.
That wasn't too long ago. And we proved that they're parallel, right? Opposite sides are parallel.
Yeah.
Okay? We're going to use that today. This is called the medial triangle, which is kind of a bad name because it makes me think of like medicenter and medians. But it's called the medial triangle because it's connecting the mid-segments. We call those mid-segments because it's connecting the midpoints. Does that make sense? You don't need to know all this terminology today. I'm just giving you an idea. Every triangle has a medial triangle, right? Because every triangle has midpoints. And we can always connect dots, right? So if I draw a weird triangle, does it have a medial triangle? Yeah, here's a midpoint. Here's a midpoint. Here's a midpoint. There's the medial triangle, right? And it'll always be in a 2-to-1 ratio. Whoops, single, right? And parallel, okay? Always true. What we're gonna do now is instead of drawing a triangle and finding its medial triangle, I'm gonna give you a triangle, and we're gonna build the triangle around it. And these will be parallel and half, right? Double and half. And these will be parallel, double and half. And these will be parallel, double and half, okay? We're gonna use that property. Every triangle, you can draw another triangle around it like that, okay?
Really? Oh
Yep.
yeah, you have to.
Right, yeah?
So would there be
You can draw another one around that.
triangle scribe?
Yeah.
Wait a minute.
It's a circumscribed triangle.
Did you say if it has 3 sides, it's a triangle, right?
I don't know what you just said.
Like if a shape has 3 sides, it's a triangle.
No. If the shape has 3 angles, it's a triangle.
So what about that up there? My corner of my football, is that a triangle? Because it's round though.
No, does it have 3 angles?
Yes.
That's 2 angles.
Yes.
It has 2 angles.
Remember, you're done.
No, it has.
Where's the 3rd angle?
Okay, if you're arguing that it has 3, then it definitely has 4.
Not that, the corners on the other side of the red.
Oh, like this right here?
Yeah.
Ooh, yeah, it is a triangle.
Target self-development.
Except it's a triangle. It is a triangle, but it's a triangle
With the curve.
in curved space.
It's a hood triangle.
So if you were to take a globe and draw a triangle on it, the angles wouldn't all add up to 180.
Oh my god,
It's a triangle in curved space, hyperbolic space, which is actually how the real world works. Most space is curved.
The
All
Earth
right.
is flat.
Hi.
Um,
Not now, though. We got to go. All right.
Can you
If
tell
the
me how
Earth
much
was
one
round,
of
the
the
water
problems
would
were?
fall off.
No.
Earth was round. How come the ball ain't going?
Why?
The Earth is a bowl.
All right, so here's what I'm going to do. I'm going to make parallel lines. I'm going to make this guy. I'm going to make a line parallel to that. Okay? The writing is actually very little, so I'm just going to create a parallel line. Okay?
Wait
They're
a
parallel.
minute, so you could argue a pro. No.
You can always make 2 lines parallel, right? I give you a line, make a line parallel to it. You could do that, right? I'm going to make this line a line that's parallel to that. I'm going to place it right here. So these 2 are parallel.
Do you
Whoops.
have to like say let there be?
Why are we
Yes.
doing this?
But it'll be okay.
Oh my god.
Well, while you were working on that, I explained why we were doing this. So we're doing this because we're going to create this triangle, which is going to be a medial triangle of a bigger triangle I made.
Multitask. Yeah, I can. Oh my god. I can multitask.
So these will be parallel. Okay? We cool with that?
I am cool with that.
If we do it in color, do we have to wait them?
So we're going to make them go into points. We're going to say let there be these guys, and they're going to intersect at D, E, and F, right? It's actually going to be a little bit, it's not a lot of writing, I promise, okay? The hardest part is creating the lines, and after that, it all falls into place. So if this is true, that means this is a medial triangle, right?
What?
Right?
Which
It's one of these guys. It's this guy.
So
And the medial triangle is always half the opposite side, right? So I know
no.
that if this and this is the whole side, right? That, right? We cool with that?
Wait, what do you mean half the opposite side? Like, can you go back to the other picture? You just
So this is double, and this is half.
yeah.
We proved that last week. That's all I need you to know. Or a couple weeks ago.
I failed that, so we'll go back later.
Right? We cool with that? So I know that to be true. If I know that to be true, doesn't that mean that B and C and A are the midpoints of the bigger triangle? They are, aren't they? So I'm allowed to go from a midpoint and draw a 90, right? So I'm going to do that.
C cannot
It's going to get messy. Are you with me? I'm going to draw a 90 degree to this orange line. We cool with that?
Sure. Oh, you did it through the big triangle.
Now watch. 2 parallel lines, and the line I just drew is a transversal. There's a sea of lines here. Focus on the orange and the red. 2 parallel lines. If this is 90, then this is 90 by alternate interior angles. Now look. Small triangle. This line right here. Ignore that. From here to here. Isn't that an orthogonal? It goes from the vertex to 90, doesn't it? right? Okay. I'm going to draw another perpendicular bisector here. Right? Totally allowed to do that.
Then you have
Two parallels, transversal. If that's 90, then this is 90.
Yeah,
Isn't that an orthogonal of my triangle? My small triangle?
it is.
The orthogonals all intersect here. And I know that because the perpendicular bisectors of the bigger triangle all intersect there. And don't the perpendicular bisectors of a triangle always intersect at one point? Didn't we just prove that?
Yes.
So, hear me out. The orthocenter of the small triangle is the circumcenter of the big triangle.
Be careful how you say that.
So I'm going to draw my next one in. Again, this is the midpoint, right? And I drew it really poorly. Midpoint should be like right here. My bad, right? If this is 90, then this is 90 by alternate interior angles. Do you guys see that?
Yeah.
Two parallels, transversal, right?
That's not a
So
exactly.
if you just focus on this line, that is the orthogonal of my small triangle. And isn't this line another orthogonal of my small triangle? And isn't this line another orthogonal? So because the perpendicular bisectors of the big triangle all intersect at one point, the orthogonals of the small triangle do too.
Say orthogonals for person.
We're going to cover this for real tomorrow.
Yes.
But do you sort of see it?
Yes, no,
That's
maybe
really
so.
good.
This today is not that bad.
Talk to first hour.
Why?
They did this without any prep, and I didn't do it in color. They cried.
Oh, that's going. Wait,
Right?
you didn't do it in any color.
Oops.
You have open bowling?
What is
I
this?
swear to God, Schlaffer. Focus on the here and now. That's the idea. So we're just going to say, let there be all these sit down. Let there be all these parallel lines, right? And have them intersect to form another triangle. By definition, triangle A, B, C, shut up and listen.
Okay.
By definition, this is the medial triangle. And medial triangles always have congruent parts, right? Right? We talked about that, right?
That's right.
So this must be the midpoint. So when I draw my perpendicular bisectors, they intersect at this point. And that naturally creates these guys, my orthogonals, by alternate interior angles theorem. Alternate interior angles. So where the perpendicular bisectors intersect to the big triangle, the orthogonals intersect to the small triangle. You're going to need alternate interior angles theorem. You're going to need to create all these lines, right? And you're going to need to know definition of a medial triangle, right? This guy. So,
You can
Great.
put a triangle in a box.
the perpendicular bisectors of the big triangle all intersect at this point, right? And notice that from here to here, that's an orthogonal of the small triangle. That's an orthogonal of the small triangle. And that's an orthogonal of the small triangle, right, from here to here. So if the perpendicular bisectors of the big triangle all intersect at one point, and the orthogonals are on those lines, right, then they all intersect at one point. Okay? Again, seeing it's the hardest part. Guys, the reason I structure my class the way I do, especially for geometry, where it's mostly you can just watch, is important. Because seeing this all at once, like if I just showed you this and it's like, look guys, you'd be like, good God, what? But if you see it slowly over time with a couple more examples of seeing it happen in front of you, it works out a lot better, which is why video is so good,
Like a painting.
right? If you are copying stuff down and then look at this at the end, you're going to go, good God, what? Why? Right? How is any of that true? Watching and seeing it is more than half the battle in geometry. I feel like it's more than half the battle for most things. Don't write, just watch.
Hey.
If I know everybody's paying attention, I'll give you a pass on the homework or whatever, right? But I want to give you 3 points.
Like,
Okay. Are you feeling okay? All right. Tell first hour there's hope if you see them. Okay.
who's in first hour? Danny Mo?
No. But anyone below, like, the further we get to 6th hour, the better the classes get. So 1st hour got it the worst. 3rd hour was sort of okay. 4th hour is really good. 6th hour is definitely the best. And yeah, math should be illegal to do that early. Go away.
I'd rather have it in the morning.
I love you all.
For the day.
Do you want me to do this whole packet?
I want you to do it all right so that I know that you can do it, and then I'll give you the quiz. Does that make sense?
Well, you told me that if I did the review without any help,